We've got a problem that compares two samples, trying to figure out which sample is more surprising, or we could say more unusual. In this problem, we have a population mean, no standard deviation, and then two different sample sizes with the same resulting sample mean. What I will do is pick my own standard deviation to use for all these problems. It really won't matter what standard deviation I pick as long as I stay consistent. And then I'll simulate what number of samples would be kind of in each of these ranges. I'm going to be using Rossman chance applet collection, one variable with sampling. This one can be difficult to find. If you're looking at the entire 2021 collection, you could look at sampling from a finite population. This is a fun one to look at because they've got different data that kind of has different skew and average and stuff like that. But the one that we want is down here at the bottom, the population model. This allows us to look at a theoretical distribution with the inputted mean and standard deviation. On this problem, that population mean is 2,600. And I'm just going to make up a reasonable standard deviation for a population of this size, 231 for mine. We don't know the shape of the data. In this case, I'll just leave it as normal. We can adjust that and see what different shapes will do. Next, we want to sample from this population. The problem that I was looking at had two samples. Sample A had a sample size of 9. Now I can draw these one at a time and take a look at what these simulated samples would look like, getting sample statistics for each one in this most recent sample area. And then on the far right, it begins to build a sampling distribution. And that is just a record of every sample mean that we've collected and stats for that group of data. So essentially, we're building a data set of sample means for this size of sample. Now I should do that by creating a whole bunch. Let's see, so far I have 4. Let's go for a total of 10,000. So I need 9,996 more to get me to 10,000 total. As predicted by the central limit theorem, the mean of all these sample statistics is very, very close to the original population mean of 2,600. The standard deviation, over on the far right, we would call it standard error. This is the standard deviation of sample means. We could estimate that by taking the original standard deviation, 231, divided by square root of the sample size. Square root of 9 is 3, so 231 divided by 3 would be about where I'm at, right about at 77. Here I've got 77.1. So here we're looking from sample to sample what we would expect to get with our 10,000 simulations. Now the question asked about how surprising would the result be if it was 2750. And just to put it into context, this problem is about grants, Pell Grant recipient amounts. So we're looking at samples of 9 people and what their average Pell Grant amounts are. It said an award of 2750. Let's put in that 2750 and count. I haven't changed the direction of the arrow at all yet. Usually I'll just plug in the number and draw the shading and count the number. And then if I'm facing the wrong way, I'll flip it around. So if I were to get this shading where it goes all the way across the middle, that's not what we're looking for. We're looking for what we would call a tail. The tail gives us a degree of uncertainty. Or we could call it, what percent of samples would be like this or more extreme. So about 2.5% of my samples landed in that range. That's pretty small. We would think of anything smaller than 5% to be unusual. We can look at the normal distribution and see what it would be with that theoretical curve as well. That is my first group. Now I'm going to repeat this process again. I'll create a new window so I don't lose that information. And repeat it with the same average Pell Grant of 2,600. I picked a standard deviation of 231. Next, I can draw my samples of 36 from this population, same population. Again, 10,000 samples. I think it's best just to stay consistent there. And I'm pretty close to 2,600, just slightly below it. Those numbers, I should be able to calculate those. 231 divided by square root of 36 is the same as 231 divided by 6. So we see that we have a smaller standard error. That means from sample to sample, we're seeing less variation, which means our 2750 should be really far out there in this case. You can kind of imagine this as we get bigger and bigger samples. Notice how the most recent sample, when I pick 9, there's not a lot going on there. There's not a ton of information to base that mean on, which means the mean from sample to sample will be less accurate. When I got a bigger sample, there's more information to go off of. So each sample mean should be closer to the middle, closer to the true mean of 2,600. Therefore, being at a certain point in this curve, when we have a small sample size, is not as unusual as when we have a larger sample size. So we could say that the result of sample B is more surprising because we see less variability from sample to sample. And therefore, this result ends up, relatively speaking, farther in the outskirts of that curve. One thing I encourage you to do on problems like this is estimate the z-score. Look at the overlay and look for the inflection point on the curve. That is where it flattens out. See how far that point is. Now I can zoom in to really point this out more. See how far that inflection point is from the middle and see how many of those distances you've gone over. Here we're looking at about a z of 2. 2 is usually easy to find because it's going to be right around where the tail starts flipping out, and then over here where it flattens over is about z equals 3. So we're at about z equals 2 on this one, whereas on this one we are well past a z of 3. So z of 1 would be directly under that inflection point. Then we'd have 2, then we'd have 3. I said well past, maybe right around that z of 3, giving us 0.01%, or only 1 out of all of those 10,000 samples that ended up over there.